So, good afternoon. Am I audible?
Yes, sir.
And can you see
Yes, sir.
the screen share?
Yes.
Okay. Now today we shall start the next chapter. That is, so far we have discussed about the forces and forces, system of forces, and the resultant of concurrent force system. Now today we shall discuss the centroid and moment of inertia. So first we shall discuss what is centroid. Then in the subsequent classes we will be discussing about the concept of moment of inertia. So the centroid and moment of inertia. So you will be introduced to the centroid of plane areas, the centroid of composite areas, and the significance of moment of inertia, and also the significance of parallel axis theorem, perpendicular axis theorem, and moment of inertia of composite area. So the heading of this chapter is centroid and moment of inertia. Now, what do you mean by centroid and the center of gravity? So, center of gravity is a point through which the resultant of all the weights is concentrated. Center of gravity is a point through which the resultant of all the weights is concentrated. Whereas centroid is nothing but it is the geometric center of the plane areas. So the main concept in centroid is, so if you consider a body of mass, correct? If you consider a body of mass, then if you consider the body is having a uniform density, then only the area comes into picture. So the volume means area into the thickness. So volume is nothing but the area into thickness. So if you consider the thickness as uniform, then only the area you are going to consider. So in engineering applications, we get many composite areas like whether it may be a rectangle or it may be a triangle or it may be a quarter circle or a semicircle or a circle. In such cases, we need to find the geometric center of the plane areas. So let us discuss what is actually centroid is all about. Now, suppose a plate of weight W can be balanced by a finger adjusting the position of the plate by trial and error method. So this everybody can do it. So if you take any book or you can balance that book by a finger by adjusting the position of the finger by trial and error method. So when the plate is balanced this way, so we can conclude that the system of forces acting on the plate is in equilibrium condition. That means in the previous chapter we have discussed when a body is subjected to a system of parallel forces. In the first chapter we have discussed when a body is subjected to a system of parallel forces which is in equilibrium condition, the sum of moments of all these forces must be equal to the moment of the resultant of the forces. So that is nothing but the concept of Verrignon's theorem. The moment of the resultant will be equal to the algebraic sum of moment of all the forces. So in the system, we have seen that when a body is subjected to a system of parallel forces, which is under equilibrium condition, the sum of the moment of all these forces must be equal to the moment of the resultant of the forces about any axis. Exactly the similar situation exists in the case of a plate. The plate can be thought of considering a number of small elements. So wherein each element has particular magnitude of weight, and the plate can be balanced only when the position of the finger coincides with the line of action of the resultant of all the weights. So that means suppose if you consider a book or any plate, so it can be divided into number of small fragments or segments, and each these fragments constitute certain weight, and each of these weight acts at the center of such individual figures. So the system of forces forms a parallel system of forces with reference to any one of the axes. So that is the introduction of the centroid. That means the center of gravity of a body. Now we can define what is center of gravity of a body can now be defined as the point in it at which the resultant of gravitational force is concentrated. So there is a difference between center of gravity and centroid. Now, so we know that the weight of a body can be determined by calculating the product of the density. So you can call it by notation rho and volume. Volume, you can call it as V. So the weight of a body can be determined by calculating the product of density. Density is mass by volume, and it is designated as rho and volume as V. Now, the volume V is again, it is a product of the cross-sectional area. Cross-sectional area is nothing but L into V, and the thickness T, the thickness T. If a body has uniform density and thickness throughout it, these factors can be neglected or it can be cancelled. And only the factor area remains in the moment equation. Now, the weight can be calculated by, it is a product of density and volume. Again, volume is again a product of cross-sectional area and thickness. And if we assume that the body is having uniform density and thickness, so these factors will have less effect and it can be neglected, and only the area remains in the moment equation. Area remains in the moment equation. Under such circumstances, the problem is reduced to determination of centroid of plane area. So we'll be dealing with the centroid of plane area. So centroid of a plane area is nothing but its geometric center. Geometric center of any type of area, whether it may be a rectangle, whether it may be a triangle, whether it may be a circle, whether it may be a quarter circle, or a sector of a circle, or semicircle, whatever may be the shape of the figure. So we are going to consider the body as having same density and uniform thickness. Only we are going to consider the area. Now, centroid of an area is a point through which the resultant of parallel forces acts. So whereas the center of gravity of a body is nothing but where the resultant of gravitational forces is concentrated, whereas centroid of a plane area is a point in it, or else it is also called as a geometric center through which the resultant of all the forces acts. Now we shall we shall understand this concept in a better way. Now you can see here, centroid of plane areas. Are you following it? ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? Hello? Hello? You people are following the concept?
Yes, sir.
Okay. Okay, now centroid of a plane area. So now let us discuss how to calculate centroid of a plane area. Now, suppose a plate or a body on XY plane as shown in figure is divided or discretized. It is also called as divided or discretized into small elements. Now you can see here, this is the body. So now we shall assume that this body is on a XY plane or a plate or whatever it may be, and it has got uniform density and thickness. Only we are going to consider the area. So this plate is divided into number of small parts, or it is discretized into number of small elements, and each of these elements constitute certain weight, that is W1, W2, W3, W4, W5. And this weight will act at the center of each elemental strip. Now here, the whole body is divided into number of small segments or small strips, and each of these strips will constitute certain weight, and this weight will act at the center of such each strip. Now, a plate on XY plane as shown in figure is discretized into small elements. The weight of each element is given by rho into area into thickness, correct? Where rho is the density, and area is A is the surface area, and T is the thickness, and the suffix N is the number of small elements. So the weight of each element is given by rho into volume, that is density into volume. Weight is nothing but it is a product of density into volume. Again, volume is a product of area into thickness, and this suffix N is nothing but the number of such small elements. Now, the forces acting on all the elements form a system of parallel forces. Now you can see here, this plate is on XY plane, and these forces, individual forces acting at the center of each strip, it forms a parallel force system, because the line of action of these forces are essentially parallel to y-axis. Now, the forces acting on all elements form a system of parallel forces, and the coordinates of the resultant of all the forces is assumed to be X bar and Y bar. So centroid is nothing but basically we are going to find the coordinate distances of the resultant with respect to x-axis and y-axis. Now, here you have system of parallel forces. You have system of parallel forces, and the resultant of all these forces will act at the center of this plate. Center of this plate. So let us call it as W. Correct? Let us call it as W. So W is nothing but it is the algebraic sum of all the individual forces, that is W1, W2, W3, W4, W5, and which acts at the center of this plate, so which is called as the geometric center. Now it is, you can see here, it is designated by a letter G. So this point is known as the resultant of all these weights. Acts at the center of this figure, and which is at a distance. Now you can see here, these are the corresponding coordinate distances of these individual weights with respect to y-axis and also with respect to x-axis. So these coordinate distances are, you can call it as x1, and this distance as x2, and this is as x3, and this is as x4, and this is as x5. That means from this center to y-axis and from this center to y-axis are x1, x2, x3, x4, x5 respectively with respect to y-axis. And similarly, the vertical distance with respect to x-axis are y1, y2, y3, y4, y5 respectively. Now, so these forces will form a system of parallel forces, and we need to find the geometric center of this plate, so which is called as G. So now, which is at a distance x bar you can see x bar, and it is y bar. So x bar is the coordinate distance of this plate with respect to y-axis, and y bar is nothing but the coordinate distances of this plate with respect to x-axis. So this x bar and y bar are nothing but the centroidal distances. The centroidal distances, or it is also called as the coordinate distances with respect to x and y-axis. Now, the coordinate of this resultant of all the forces is assumed to be x bar and y bar as shown in figure. Now, so what we have done is we have considered a plate, and this plate is discretized into number of small elements, and each element constitutes certain weight, and this weight acts at the center of each such individual elements, and the corresponding distances with respect to x and y axis are x1, x2, x3, x4, x5, and y1, y2, y3, y4, y5 respectively. Then when you take the moment of all these forces with respect to x axis and y axis, we are going to find the x coordinate and y coordinate of the given figure. So that is, this x and y coordinate are nothing but the geometric center of the given figure. Now, we know that the sum of moment of all the parallel forces should be equal to the moment of the resultant. Now, here we are using the concept of Verigneaux's theorem. That means the moment of the resultant about any point is equal to the algebraic sum of moment of the individual forces about the same point. So the same concept we'll be using here. So we know that the sum of moment of all the parallel forces should be equal to the moment of the resultant of the forces about the same axis or about the same point. Now, let us take the moment about the y-axis again. Now, let us take the moment of all these forces with respect to y-axis. Now, that is nothing but we want rho into t into a. That is rho into t into a. That means we are going to consider the whole body. So here rho stands for density, and t stands for thickness, and a stands for area, multiplied by this x bar. X bar is nothing but the coordinate distance with respect to y axis. So we want this x bar. So let us take moment of all the forces with respect to y axis, and also the moment of the resultant about the same axis. Now, rho into t into a into x bar is equal to rho into t into a into x1, rho into t into a into x2, rho into t into a into x3, plus rho into t into a into xn. So you may have any number of elements. Now, assume that the density and thickness to be uniform throughout the body, thus reducing it to a plane area. Then the equation is reduced to, now we are going to consider the density and thickness as uniform. throughout. So we can neglect these rho and t, and only the area remains in the moment equation. Now ax bar is equal to a1 x1 plus a2 x2 plus a3 x3 plus dash 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 an xn. So now we want the coordinate distance with respect to x-axis. That is, x bar is equal to a1 x1 plus a2 x2 plus a3 x3. This whole divided by the total area of the figure. Total area of the figure. So, or else it can also be written as x bar is equal to sigma ax divided by sigma a. Sigma a is nothing but the area of the whole figure. The area of the whole figure. So similarly, considering the moment of all these forces with respect to x-axis. Now we can take the moment of all the forces with respect to x-axis. Then it becomes ay bar. Ay bar is equal to a1 y1 plus a2 y2 plus a3 y3 plus dash 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 an yn. So hence y bar is nothing but a1 y1 plus a2 y2 plus a3 y3 divided by a, or you can also write it as sigma ay divided by sigma a. So these are nothing but the coordinate distances with respect to y-axis and with respect to x-axis. So centroid is nothing but the geometric center of any given figure. So x bar is always measured with respect to y-axis, and y coordinate distance is always measured with respect to x-axis. So what we have done is we have considered a plane area. Let us say we have considered a plane area on xy plane, and this plane area is divided or discretized into number of small elements, and each element constitutes certain weight which acts at the center of that particular elemental area, and the corresponding distances with respect to x and y axis are x1 y1 x3 y3 and like that, x1 x2 x3 xn and y1 y2 y3 xn. So when you take the moment of all these forces with respect to any reference axis and equate it to the moment of the resultant, then we get this expression, that is ax bar is equal to a1 x1 plus a2 x2 plus a3 x3. So thereby you can find the x coordinate distance with respect to y-axis, and similarly we can find the y coordinate distance with respect to x-axis. So this x bar and y bar are nothing but the coordinate distances with respect to both axes, whether it may be x-axis or y-axis. So therefore the equation of centroid of an area is given by the coordinates. These coordinates are nothing but x bar and y bar. So any doubts with this concept? Anyone? So basically, the definition of center of gravity is nothing but center of gravity is a point on Earth where the resultant of gravitational force is concentrated, whereas centroid refers to plane areas, or it is also called as the geometric center. So this geometric center is located at a distance of x bar and y bar from the respective axes. So this x bar and y bar are nothing but the coordinate distances. Now, so this x bar and y bar are nothing but sigma ax divided by a and sigma ay divided by y. Now, the location of centroid can also be determined by the method of integration. So here we will be using the mathematics, where by integration method also we can find these coordinate distances, that is x bar and y bar. So here we have used the concept of moment to find the x bar and y bar of a given plane area, and the centroid are the coordinate distances of any given figure, any given plane figure can also be determined by using the concept of mathematics, that is the method of integration. So the location of centroid can also be determined by the method of integration, that is the summation of moments related to small elements. The equation for the determination of the location of centroid are given by, so ax bar is equal to integral of x dA and ay bar is equal to integral of y dA. So here this is a more general expression where ax bar is equal to a1 x1 plus a2 x2 plus a3 x3. Now here we have used the moment equations, whereas in case of integration, so we are going to determine the moment related to small element. We are going to consider a small element and it will be integrated between the limits, in order to get the values of x bar and y bar, the coordinate distances. Now, centroid of geometric shapes. The location of centroid of various regular shapes like triangle, circular, sector, semicircle, etc. can be determined by using the equation 8.4, that is by the method of integration. Hence, the determination of location of centroid of a plane area involves the determination of x and y coordinates of the centroid of the area lying on xy plane. Now, we shall discuss how to locate the centroid of various geometric shapes by the method of integration. So first, we should start with a triangle. Now you can see here, triangle. The figure shows a triangle on XY plane. So here you have a right angle triangle ABC on XY plane, whose base is B and height is H. The height is H and base is B. Now, we shall now find the location of the centroid with reference to the base, considering an elemental area of depth dy at a distance y from the base. Now, first consider a triangle, right angle triangle ABC on XY plane and whose base width is B and height is equal to H. Now, let us find the centroid of this right angle triangle with respect to base. Let us find the centroidal distance of the triangle. So this is the centroid of the given triangle. Now let us find the centroid of the right angle triangle with respect to base. So by the method of integration. Now let us consider a small elemental area. Now let us consider a small elemental strip having a width W, and which is at a distance y from base, because we are finding the centroidal distance with respect to base. So consider a right angle triangle on XY plane whose base is B and height is equal to H. Now let us consider a triangular element, let us consider a small elemental strip of width W, so which is at a height y from the base, and the depth of this small elemental area is dy, the depth of which is dy, and it is having a width is equal to W, so which is at a distance y from the base, and it is at a distance h minus y from the apex, So this elemental area having depth dy and width is equal to W. Now let us find the centroid of the right angle triangle by the method of integration with respect to base. Now you have two triangles here. One is ABC and the other one is BDE, correct? You have two triangles here. So from similar triangle ABC and BDE, the width of the element is given by, now the width W. So here W by B is nothing but H minus Y by H, correct? W by B is equal to HY minus H. And area of this elemental strip, we shall call it as dA. Now, the area of this elemental strip dA is nothing but W into dy. So area of the elemental strip is dA is equal to W into dy. So from the similar triangles, W is nothing but W by B. So W by B is nothing but HY divided by H, or W is equal to H minus Y by H into B. So now area of the elemental strip is W into dy. So we know what is W. W is nothing but H minus Y divided by H into B. So if I substitute W as H minus Y divided by H by B, so the equation becomes W into dy, that is nothing but H minus Y divided by H into B into dy. Now we know that AY bar is nothing but integral of y dA. So this is the equation we will be using. ax bar is equal to integral of x dA, and ay bar is equal to integral of y dA, because we are finding the centroidal distance of this right angle triangle with respect to height, with respect to base. It is with respect to base here like this. So hence we need to use ay bar. So y bar is always measured with respect to x-axis, and x bar is always measured with respect to y-axis. So in our case, we are considering the x-axis as reference to find the centroidal distance. So hence we'll be using ay bar. Ay bar is equal to integral of y dA. Integral of y dA. Now, what is the area of the triangle? Half into base into height into y bar. Half into base on the left hand side, area is nothing but half into base into height into y bar is equal to integral. So we have to integrate this elemental string, and the limits of integration is 0 to h. So integral of 0 to h into y into dA. So dA is nothing but this one. dA is nothing but h minus y divided by h into b into dy. Now, integral of 0 to h into y into b by h into h minus y into dy. So now you can take b by h outside. B by h outside. So b by, if you take b by h outside, it becomes hy square by 2 minus y cube divided by 3. So if you integrate this, so take b by h outside the integration. So that is h into y minus y square dy. If you integrate h into y minus y square dA, so that is nothing but hy square divided by 2 minus y cube divided by 3. And the limits of integration is 0 to h. 0 to h. Now, on the left hand side, you have half into bh into y bar, half into bh into y bar. So if you apply the limits of integration, it becomes bh square by 6. So bh, so if you substitute y as h, correct, h cube divided by 2, h cube divided by 3. So on simplification, you will get it as bh square by 6. bh square by 6. Now you want this one, y bar. So y bar is equal to bh square by 6 into 2 divided by bh. So b gets cancelled. H square here. So finally, the location of centroid from the base y bar is equal to h by 3. So now you can see here, this is the figure, right angle triangle whose base width is v and height is equal to h, and the centroidal distances of this right angle triangle with respect to base along the height, it is h by 3 from the base, and it is 2h by 3 from the apex. Suppose if you consider y bar, its centroidal distance with respect to y-axis. So if you consider y-axis, the x bar will be the centroidal distances of this right angle triangle with respect to y-axis is b by 3 from the base, and 2b by 3 from the apex. So either you can find the centroid of the given triangle either with respect to base or either with respect to height. So here in our case, we have found the centroid of the right angle triangle with respect to base, so which is nothing but h by 3 from the base. So this is the point geometric center of the triangle, so which is at a distance h by 3 from the base and 2h by 3 from the apex. So similarly, if you consider base, if you consider b, it is at a distance of b by 3 from the base and 2b by 3 from the apex. So by the method of integration, we can find the geometric center of the any given figure. So today we have discussed how to locate the geometric center of a given right angle triangle by the method of integration. So the time is running out. So I request all of you to mark your attendance in the chat box. So I'll continue the class tomorrow. So tomorrow we shall discuss how to find the centroid of a circular sector, and also how to find the centroid of a semicircle, and how to find the center of a quarter circle by the method of integration. So I'll be ending the session. So thank you so much. Any doubts? So tomorrow once again I will explain how to locate the centroid of a right angle triangle by the method of integration. So anyway, I'll be ending the session. ಕಾನ್ಸೆಪ್ಟ್ ಕ್ಲಿಯರ್ ಇದೆಯಾ? ಯಾರಿಗಾದ್ರು ಡೌಟ್ಸ್ ಇದೆಯಾ? ಹಲೋ, ಸ್ವಲ್ಪ ನಾನು ಹೇಳೋದು ಫಾಸ್ಟ್ ಇದ್ರೆ ಐ ವಿಲ್ ಸ್ಲೋ ಡೌನ್ ದಿ ಪೇಸ್. ಹಲೋ, ಐ ಆಮ್ ನಾಟ್ ಗೆಟಿಂಗ್ ಆನ್ಸರ್ ಫ್ರಮ್ ಯು ಗೈಸ್.
No doubt, sir.
Is it clear? So anyway, we shall meet tomorrow. I think you have my class at 11:40. So till then, have a nice day. Stay safe. Take care. Goodbye.